On-target prototyping and internal bypassing with the dSpace RTI bypass block set. The dSpace RTI bypass block set enables model-based function development and rapid prototyping using the bypass approach. Apart from the well-known external bypass method, the dSpace RTI bypass block set also supports internal bypassing and on-target prototyping. This video shows you how to use the RTI bypass block set in the service-based internal bypass approach. With the internal bypass approach, the RTI bypass block set lets you implement and prototype bypass functions directly on your target ECU, utilizing free RAM and flash resources. New functions are integrated directly in the compiled ECU software. There's no need for source code or the build environment. Based on the bypass hooks implemented in your target ECU software, you can intuitively configure your bypass application in Simulink and define flexibly where to integrate your bypass functions and when to read and overwrite ECU variables. Depending on your application, you can use the external or internal bypass approach. When requirements change, simply switch from one to the other with no changes to your bypass model. To understand how model-based bypassing works, let's have a look at this example. This is a Simulink model that implements a bypass function for an internal bypass. First, the bypass interface has to be configured. In the Setup dialog, you need to pass information on your target ECU to the model using an ECU variable description file in A2L format. You can also add an additional A2L file that contains information about the bypass service and hooks implemented in the ECU. This file is typically generated with the ECU Interface Manager. In addition, select the bypass interface type and configure it. In the configuration dialog, you can define the C compiler for your target ECU and the name of the A2L file to be generated. The signals and parameters of your internal bypass model are automatically integrated in this file. You also have to define the name of the new hex file that includes your internal bypass function merged with the bypass service and hooks and the original ECU hex file. The RTI bypass interrupt block specifies the bypass hook in the ECU code which triggers your bypass function. Here, you map the trigger to a corresponding bypass hook. Now let's have a look at the bypass function subsystem. The new function that you are going to design is connected to bypass read and write blocks. The read block reads ECU variables and passes the associated values to your bypass function as input signals. After the calculation of the bypass function, the associated output signals are written back to the ECU by the write block, for instance by overwriting ECU variables. In the RTI bypass read and write blocks, you can specify when to trigger the read and write operations by choosing the corresponding bypass hook and selecting the ECU variables to read or write. An option to enable or disable bypass hooks during runtime makes it easy to compare your bypass function with the original one. Finally, build your application and flash it to your ECU. Whenever you need information about your bypass model, like the resources currently used by your bypass function or the size of your ECU's free RAM and flash areas, you can use the bypass info block. Now you're ready to evaluate your new function directly on the target ECU. On